Welcome back to the course Basics of Mechanical Engineering 3. We were discussing fluid mechanics in the second half of this course. I have taken tutorials, we have discussed the concepts of the fluid mechanics that Professor Ramkumar has discussed in his lectures. This is a tutorial where I will further discuss about laws of fluid mechanics. I discussed about the Pascal's law, the Bernoulli's equation in the last tutorial. Here I will talk about Kiewit equation. I will talk about flow rate, I will talk about Prandtl number. I will talk about certain other laws or concepts which are important in fluid mechanics. This is the last tutorial session of the course. I am Dr. Amandeep Singh Oberoi from Indian Institute of Technology, Kanpur. To recall the concept of Kiewit equation, the Kiewit equation arises from study of Kiewit flow, which describes the laminar flow of a viscous incompressible fluid between two parallel plates where one plate moves tangentially relative to the other, inducing fluid motion purely by shear stress. The Kiewit equation, here you can see we have velocity distribution of the fluid. In mathematical expression, the velocity distribution of fluid between two parallel plates where the lower plate is stationary, upper plate moves at a velocity u. This is given by u y, that is fluid velocity at a distance y from the stationary plate. This is equal to u y by h, where u is velocity of the moving upper plate, as it is mentioned, it is upper plate moving velocity. H is the distance between two plates, and the velocity is being taken at a distance y. This is distance y from the stationary plate. So, this formula shows a linear velocity profile across the gap. Kiewit equation has real life practical applications such as for journal bearings. In bearings, there are bearing balls and bearings are there. There is always a gap between bearing and the ball. There is a lubrication between them. There, when it is running at very high RPM, maybe 10,000 RPM. So, there Kiewit equation determines that what should be the distance between the ball outer surface and the bearing inner surface of the ball void that is there. Maybe some other examples could be hydrodynamics of earth surface itself, earth inside, earth crust itself. Then in chemical reactions as well, in chemical engineering certain applications are there. So, now to understand Kiewit equation, I will try to read this problem statement, and with the figure that I will draw, you will be more clear with what Kiewit equation is specifically talking about. Here it says a viscous oil with dynamic viscosity of mu 0.03 Newton seconds per meter square is placed between two large plates which are 12 millimeter apart. Distance between plates is given, that is we have value of h as 12 millimeter. The lower plate is fixed while the upper plate moves with a velocity of u is equal to 5 meters per second. The width of the plates is denoted by b, which is 0.5 meter each. Assuming steady and laminar flow, find the velocity at point 4 mm from the fixed plate. Now, what is it asking? So, we have two plates which are around 0.5 meter each. This lower plate is fixed, I will say lower fixed plate, and we have upper, or I would say moving tangentially plate. This is also a solid plate. We have thickness of the plate given as 0.5 meter each. This is 0.5, this is also 0.5. And they say distance between two plates is 12 mm only. So, this is distance between two plates. So, this distance, if I say this is 12 millimeters only. And the movement of the plate is at the speed of or at the velocity of 5 meters per second, as the upper plate is moving at this speed. Though the plates are moving, so I'll just put all the given variables here. We have dynamic viscosity, that is mu, which is 0.03 Newton seconds per meter square. Then we have plate separation, which is H, that is 12 millimeters. Then we have upper plate velocity. I will denote this as capital U. This is 5 meters per second, and plate thickness is 0.5 meter each. We might not even require thickness here, because if you see the relation here of the velocity distribution, where fluid velocity at distance y is u y by h, that's all. So, we have u here, velocity. So, let me put the relation here. Point location at which we need the velocity, that is y, this is equal to 4 millimeter. It is given in the question at 4 millimeter here. So, which means this is equal to, in meters I will put it as 0.004 meter. Now, putting the relation here, u at y, where u is my fluid velocity at a distance y from stationary plate, is equal to velocity at which upper plate is moving times the ratio of y and h. Putting the values, velocity is 5, value of small y is 0.004, value of h is 12 millimeters, which is equal to 0.012 meters. So, I will put 0.012. This turns out to be 1.67 meters per second. That is at a point 4 mm. For example, at this point, right, I will put this point in a different color. At this point, which is only 4 mm above the lower plate, the velocity u at 4 mm is 1.67 meters per second. This was very simple problem statement of a equation. Now, I will come to the Hagen-Poisson flow. When we talk about heating, ventilating, air conditioning systems, when we talk about flow of blood in body, or when we talk about many such applications where there is a relationship has to be determined between pressure drop and volumetric flow rate of a flow, Hagen-Poisson flow law is used in draining system as well to understand the fluid, how does it go in spaces, how does it go in shunting some tubes. So, all these system is used. What it states is that pressure drop is directly proportional to fluid viscosity and the pipe length, and it is inversely proportional to the fourth power of pipe radius. This results in a parabolic velocity profile of the fluid flow in the pipe. So, the Hagen-Poisson flow equation is given in this way. You can see it here. It says Q is equal to pi into delta P into R power 4 by 8 eta L. It says the flow is directly proportional to fluid viscosity. You can see in the equation Q is here and we have eta and L in the bottom. That means if I say delta P, that I talked about, delta P, that is pressure drop. Pressure drop is delta P. It is directly proportional to viscosity and pipe length. That means delta P
is equal to Q8 eta L by pi r power 4. Here we can see this, it is directly proportional to viscosity, it is directly proportional to the length of the pipe, and it is inversely proportional to the radius of the pipe, that to the fourth degree of that. This is what Hagen-Poisson flows. And then when these theories are developed, these are developed through certain experiments, and when those experiments have replication, those have interchangeability, it becomes as a theory. This is how we turn the experiment to the theory when it is replicated multiple times. So, Hagen-Poisson as a scientist developed this theory and this relationship between the volumetric flow rate and the relationship of that with the pressure drop, radius of the pipe, the dynamic viscosity and length. So, we see here R is radius of the pipe that we are talking about. P1 and P2 are the inlet and outer pressure. The delta P is the difference between these two, that is P2 minus P1. Let me see a problem statement. It says a fluid flows through a tube of radius 3 meters and length 8 meter. Determine the pressure across the tube ends if the flow of liquid is 10 cubic meters per second. It has viscosity of 0.0056 Pascal second. So, we have a pipe through which the fluid is flowing. It says it has length of 8 meters. There is an 8 meter length here. And radius it says is 3 meters. Radius is from the center, this is 3 meters, and my point of interest also becomes 3 meters here. Now, through this pipe a fluid flows. When the fluid flows, it says the viscosity of the fluid, that is eta is 0.0056 Pascal second, and fluid flow rate here, that is Q is equal to 10 cubic meters, that is 10 meters cube per second. So, putting all the values here, Q is equal to 10 meters cube per second, viscosity, that is eta is equal to 0.056, value of R is 3 meters, length of the pipe L is 10 meters. We need to find the pressure across tube ends. Pressure across tube ends means if it is P1 here and P2 here, we need to find P2 minus P1, that is delta P is to be determined. Just to put the relation once, we know Q is equal to pi delta P r power 4 by 8 eta L. That means delta P is equal to Q into 8 eta L by pi r power 4. Putting the values, value of Q is 10 into 8 into eta is 0.056 and length is 8 meters by pi into r power 4, 3 power 4. This value turns out to be 0.1408 Pascals, because everything is given in meters and seconds. It is SI units. Delta P is equal to 0.1408 Pascals. So, one quick another problem statement in the similar fashion is here, which says calculate the average blood speed when the blood flows through a large artery with the radius of 2.5 millimeter. It is discovered to be 20 centimeter long. 380 Pascal is the pressure across the end of the arteries, and blood viscosity is given as 0.0027 newtons seconds per meter square. So, it is an artery, they say. Through the artery blood flows. When the blood flows, it says discovered 20 centimeter long artery here. So, it is a 20 centimeter long artery and its radius is given as 2.5 millimeters, and here the blood is flowing at a rate, right, I would say blood flow with a pressure across the artery ends. It is from the start and the end of the artery. If this is P1, this is P2, we have P2 minus P1, which is delta P. This is equal to 380 pascals. Blood viscosity is also given. Putting down all the given variables, eta, that is blood viscosity, is equal to 0.0027 newtons seconds per meter square. We have the length as 20 centimeters, which is equal to 0.2 meters. The radius is given as 2.5 millimeters, that is 2.5 into 10 raised to power minus 3 millimeters, and delta P, that is the pressure across the artery ends, is 380 pascal. This could be directly put in the given relation of the volumetric flow rate of a viscous fluid through cylindrical pipe, which is pi delta P r power 4 by 8 eta L. You put the values and get the answer. I am only giving you the final answer. You will get the value of Q as 1.079 into 10 raised to power minus 5 meter cube per second. Or if you wish to calculate this in centimeters, I can even put it as, or this is 10.79 centimeter cubes per second. Next is Prandtl number. Prandtl number is a number that tells you how fast the momentum, that is movement, spreads compared to the heat spreading inside a fluid. It compares how quickly the fluid's velocity changes with how quickly its temperature changes. That is, when we talked about the thermal science or thermodynamics, there also I talked about Prandtl number, but it also talked about the flow of the fluids. When we talk about the flow of the fluids and its relation to the temperature, then Prandtl number is more important. When we talk about the real life applications of a Prandtl number, in real life the Prandtl number is useful to provide insights to the relative thickness of the thermal and velocity boundary layers. Thermal boundary, velocity boundary. In, for example, heat exchangers, there was velocity of the fluid, there was also the thermal temperature drop or temperature rise. There Prandtl number is an important factor to be considered. Now, if Prandtl number is large, the fluid velocity changes slower than its temperature. If Prandtl number is small, the heat spreads faster than the velocity change. You can see for certain fluid types, typical Prandtl number values are given. For liquid metal, it is from 0.004 to 0.03. For gases, 0.7 to 1.0. For oils, it is from 50 to 1 lakh. It all depends upon the viscosity of the oil here. Oil is a very broad term. For glycerine, it is from 2000 to 1 lakh. For seawater, it varies from 7.2 to 13.4. For regular water, it varies from 1.7 to 13.7. Now, Prandtl number formula is given by PR, that is nu by alpha, that is kinematic viscosity by thermal diffusivity. This part also we have discussed before, where equations of kinematic viscosity and thermal diffusivity are given here. Kinematic viscosity is mu by rho and diffusivity alpha is K by rho into Cp. If we put this values in equation of PR here, this relation turns up as PR, that is Prandtl number, is equal to mu Cp by K. Now here K is thermal conductivity, mu is dynamic viscosity and Cp is specific heat of fluid. In the case of boundary layer flow, the Prandtl number is given by PR is equal to delta by delta T cube, where delta is hydrodynamic boundary layer thickness, delta T is thermal boundary layer thickness. Now, let me see a problem statement here. It says water is flowing over the heated plate. The Prandtl number of water is 6. Find the relation between velocity boundary layer thickness and thermal boundary layer thickness. It is directly problem that he has given. They have say water is flowing over a heated plate. There is a simple heated plate here. This is a heated plate over which there is a flow of water. This is water flow, and we have velocity boundary layer and thermal boundary layer. Velocity boundary layer, and we have the thermal boundary layer. This is thermal boundary layer. Now it says Prandtl number of water is 6. Just find relationship between velocity boundary layer and thermal boundary layer. So we can just put it as PR is given as 6, and we know PR has many relations. When we have given the hydrodynamic boundary layer thickness and thermal boundary layer thickness, this is the relation that holds, that is, it is delta by delta T par 3, which means 6 is equal to delta by delta T par 3. Therefore, delta by delta T is equal to cube root of 6, which is 1.817. So, therefore, we can say velocity boundary layer is 1.817 times the thermal boundary layer thickness. So, I am talking about thickness here, velocity boundary layer thickness. Another problem that asks about the calculation of Prandtl number for a fluid when we have been given the dynamic viscosity, specific heat at constant pressure and thermal conductivity as these values. Here we can simply see we have with us mu as 0.001 Pascal second. We have with us Cp as 4200 joules per kg Kelvin. We have with us thermal conductivity as 0.6 watts per meter Kelvin. Similar problems had been taken in the thermal science tutorial as well. Here PR is equal to mu Cp by K, that is the thermal conductivity. This is our K, thermal conductivity. So, simply putting the values, this is 0.001. No unit conversion is required here. This multiplied the value of Cp, that is 4200 by K is 0.6. This turns out to be 42 by 6 is 7, and all the decimal places being adjusted, it turns out to be exact 7. That is, 7 is the number. You can see there was a table where the water number varied from 1.7 to 13.7. So, here you also see 7 is the Prandtl number value for typical water at room temperature. Next is flow rate, that is the last topic of the lecture. The volumetric flow rate is the measure of volume of fluid, that is liquid or gas, that passes through a specific point or cross section area per unit time. It is simply flow rate, a rate of flow per unit time. Flow means velocity or volume. Here we are talking about volume here. It essentially quantifies how much space the fluid occupies as it moves through a system in a given time interval. It usually is denoted by the symbol Q. Like for example, the fluid is flowing from this pipe. If it is completely filled, if it is completely flowing through this, depending upon the diameter of the pipe, flow rate could be calculated. Now, flow rate is simply given by the formula Q is equal to A into V, where Q is volumetric flow rate, that is in cubic meters per second. A is the cross section area of the flow and V is velocity of the fluid. It is very simple formula, Q is equal to A into V, provided the flow comes through the whole diameter or the whole area of the pipe. So, here you can see it is not coming for the whole pipe. Diameter when I say, diameter is proportional to area. So, it is area times velocity. So, it is very simple relation that you have been studying maybe in your senior secondary education as well. So, let me take a simple problem statement here. Water flows through a circular pipe with an internal diameter of 4 cm and a velocity of 3 meters per second. Calculate the volumetric flow rate Q through the pipe. It is a very simple problem. We have a pipe here through which water is flowing through. When the water is flowing through, it says the diameter of the pipe is 4 cm. It is 4 cm and water is flowing at the rate of V. It is flowing at the rate of 3 meters per second and water is flowing in this direction. Now, simply from the diameter I will calculate the area. We have D is equal to 4 centimeter, that is equal to 0.04 meters. Then we have velocity is equal to 3 meters per second. We know Q is equal to A into V. For that I have to calculate A. A is equal to pi D by 2 power 4, that is pi r square. This is equal to pi into 0.04 by 2 square. I got the value of A as 1.256 into 10 raised to power minus 3 meter square. Q, that is flow rate, is equal to area into velocity. This is equal to 1.256 into 10 raised to power minus 3 times velocity. Velocity given is 3 meters per second. This turns out to be 3.768 into 10 raised to power minus 3 meter cube per seconds.
With this, I am closing my lecture. This was the last tutorial session. In this tutorial, I have discussed about the flow rate and certain laws of the fluid mechanics. I will meet you in the next lecture where I will talk about the laboratory demonstration in fluid mechanics. Thank you.